So we are pretty much after today wrapping up kind of the first half of this class, which has been on energy methods. So strain energy, total potential energy, equilibrium, stability, variational approaches to deriving governing equations, and then approximate methods to approximating solutions to equations. All these revolved around starting with an energy. So because we're wrapping up this part, I'm going to we're going to have our midterm exam that was scheduled for next Thursday, and what I've decided to do is to make it a take-home exam that you can spend from today until I'll have it due next Friday. Let me share my screen so you can see. I meant to send this out to you this morning, but my work computer is on the fritz. So this is, your exam is going to look like this. It's going to be due next Friday. I think it'll be challenging, in part because I have to make up all the problems. But I am giving you a lot of leeway with this exam. I'm kind of recognizing that we're in a brave new world here. And so what I'm allowing you to do is use any of your notes, any book, including our book or any book that you find, online resources, videos, YouTube stuff, whatever you can find. You can use Mathematica or Matlab. All I'm asking you to do is to cite your sources. So if you use a YouTube video and you use Mathematica to solve a problem, tell me and include your code. The only thing I'm trying to restrict you from doing is working with someone else. And that is just to kind of, so that I can gauge you and provide you a grade on your performance on this portion of the class. So you're welcome to go read deeply or read broadly, look through our old videos, whatever would be helpful. There's 5 problems. This one is going to be something with variational calculus. The second one is going to be something with approximate methods and Fourier series. The third one is a stability problem. The fourth one is a Castigliano theorem problem. And the fifth one is some kind of general conceptual questions that we've covered that I'm looking not for theory, I'm looking for you to describe things in words. Like if someone was to ask you, like, hey, so-and-so's an engineer, she might know the answer to this question. Show me that you know the answer to the question. So this is what your exam looks like. I can't help but notice the flurry of emails I get around 11 p.m. on the night that things are due. I would recommend you not wait until next Friday to start this. I think it will take you longer than the typical homeworks. So my recommendation to you would be not to put it off. You know, try to finish it, and then maybe even give yourself a second time to look at it and check your answers. Yeah, I guess that's all I have to say about that. Any questions about this? Oh yeah, make sure that you, a lot of my homeworks are all labeled the same thing, which is like homework 3, ME309. So if you could put your name somewhere in the file name, that would be helpful. But any questions about the exam? I don't really know how to give successful exams in a world where most people are remote, and so this is my attempt. I'm trying to make it as similar to what engineering problem solving is like in the real world, in which you have a hard problem. You have all the books you can find and all the helps that you can conjure up. And I'm hoping that you'll use those resources, learn a bunch of stuff, and get the right answer. So, questions? Nothing? Really good questions on exams. All right, so it's due next Friday, the end of the day, so the 12th. So this was normally going to be an exam on the 11th, but I pushed it back to give you that extra day. Hopefully it doesn't ruin your Friday night. But started early. So how did people find the homework that was due last night?
It got a little tricky towards the end, trying to do the integration by parts.
Yeah, absolutely. That is one of those things that gets easier with practice, and when you do variational problems, you get plenty of practice with it. And it's really powerful. Even this, you're doing it all in 1D, so for a beam, so integration by parts in like dx, but it can be extended to 2D and 3D. It's actually really related to stuff that you probably learned in like a multivariate calculus, like what is it? The divergence theorem. It's kind of connected to the divergence theorem, in which you have like a integration over the body and then like an integration over a boundary. That's kind of what we're doing here. We have like the integration over the beam and then the terms that are the boundary conditions. So my hope is that you got something that looked like, you don't have to correct me if I have this wrong. My hope is it's something that you got some sort of answer in which you had two differential equations. You notice that U and W were uncoupled from each other. That means this problem was linear. So if we can solve for U, we can solve for W, we can solve the whole thing. So you should have had something which looked like U double prime of X minus F of X is equal to 0 as one of your two governing equations. Oh, there should be an EA over here, shouldn't there be? EA. And you probably had something that was like EI times the fourth derivative minus Q of X is equal to 0. These look familiar? The bottom one is a famous equation. I wrote it on your on our notes last class. This is what's referred to as the Euler-Bernoulli beam equation. Bernoulli. I think that's right. It's weird. And it describes the small deflections of beams under distributed and point loads. You're going to solve on your midterm exam for the governing equation for beams that are undergoing large deflections. So the general, more general version of this equation, it's what's known as the elastica. And it's like, if you're trying to describe the shape, that's terrible. There we go. Yeah, it's a wire. So if you're trying to describe the really large deformations of something like this, obviously the slopes here are not small. So what do? And the elastica equation is what can solve this thing. It's one of the most important equations in, actually perhaps in applied math in general, mathematics. It led to, it's the reason why variational calculus was created, why the mathematics behind a whole field of elliptic integrals and elliptic curves were used. It's the equation that describes everything from, it's the equation you would solve if you're trying to build a boat and make smooth curves all the way along the side. You're going to have the elastic equation describing those curves for the hull. It can describe the shapes of hair, shapes of transatlantic pipelines that you're laying to pass information back and forth from Europe to America. I'm not asking you to solve that equation because it is solvable. It's incredibly hard, but it has an analytical solution. But I want you to just derive the equation using the tools we've had. The thing that you'll notice, and probably the part that was tricky for folks, is let's think back to what we know about derivatives, differential equations. This one has two derivatives of u with respect to x. This one has four derivatives of w with respect to x, second order and fourth order respectively, which means you need two boundary conditions on u and four boundary conditions on w. If you have all of those, then you have a complete system that you can solve. And we could go into Mathematica and we could solve these equations and see what the shape of the beam looks like for various loads that it's under. What I think is important, and this is why it was a big part of the homework, is you know some of the boundary conditions on this thing. So for instance, you know that u at 0 had to be exactly 0. That's a kinematic boundary condition that was in place due to the geometry of the setup. I'm saying this is a clamped beam, it's clamped in the wall, there cannot be any lateral or vertical deflection there. Similarly, you know that this beam can't vertically deflect at the wall, and we said it was clamped, which means it's got to come in with no slope. No slope means that the first derivative of your deflection is equal to 0. So those three are given. I didn't say them outright, but they're given by the geometry. If you see clamped, that's what that means. So the ones you found looked a little different. Let's see what I can remember. My memory of this problem says something like EI times the second derivative of W at L. Is that equal to 0? Can anyone check what they did last? I know that it was something like EI third derivative and EI second derivative. I can't remember if there's a Q doesn't appear. No, it just should be that, right? Are these right? Who can check what they did last night? What's that?
I think for the third derivative, the only thing that's missing is the first iteration of W at oh no.
You mean like the delta?
Delta.
Yeah, so that, all right, so I think what you're saying is you had something like that at L. Yeah, okay. And since that can be arbitrary, what we end up saying is that if that can be arbitrary, then the thing that multiplies that has to be 0, and that's why that ends up going away. So do people get that idea that the virtual, in this case it's a virtual slope. What it's saying is we're allowed to have an arbitrary slope at that endpoint. There's nothing restricting that slope. Whereas at the clamped endpoint, we're not allowed to have an arbitrary slope because we know that the slope has to be exactly 0. So it's not allowed to have an arbitrary slope there. On the free end, slope might be something. We don't know. It could be some arbitrary value. So if the product of the stuff in blue and the stuff in green has to be equal to 0, then what we're left with is that this should be equal to 0. This boundary condition is pretty straightforward. What does this one mean? Let me remind you of our constitutive relationship for bending, which says that EI times curvature equals our moment. Yeah, so what was said in class here is that this boundary condition here means that the moment at the free end of the beam is 0. In other words, there is no applied moment at the free end of the beam. There has to be no, that means the curvature at the end of the beam has to be exactly 0 because there's no couple being applied at the end of the beam there, which makes sense. Our drawing didn't have a couple there. There shouldn't be a couple there. The one you might not remember from mechanics of materials, which had to do with the deflection moment shear force relations, is that the third derivative of deflection is your shear force. People remember that? Maybe. First derivative is slope, second derivative is curvature. Sorry, first derivative is slope, second derivative is moment, third derivative is shear force. We did all those like, shear force along the end of the beam, moment along the end of the beam. That's all this. It's all the same thing. So this first boundary condition says there's no moment at the end of the beam. The second boundary condition says there's no shear force applied at the end of the beam. And that means that basically what that means is if you have your clamped beam, a shear force would be something like that. A point load at the end of the beam. We have no point load at the end of the beam, so there can't be any shear force at the end of the beam. So that has to be 0. So these are the boundary conditions that we found just by solving the problem. And this top one up here is telling us that there's kind of no stretching at that last point of the end of the beam. So the point at L, there's nothing kind of pulling on it to stretch that last point, which makes sense. If you look at our beam the problem that you solved, there was a distributed force all along the beam, but there was no point force pulling on the end of the beam, right? There was not this situation. That didn't exist, and that boundary condition is saying, yeah, there can't be any point force over there. If there was a point force, then you would have that is equal to P. Boundary conditions would change, the solution to your problem would change. How are we doing? Is this sound all right? Which one was this? This was homework 3. All right. This is the last lecture on problems relating to energy. And it's a weird lecture for me to give. I kind of struggle with it because it's on a topic that, in all likelihood, many of you won't use or really work with too much again. I'm not asking you anything on the midterm about it. I'm not asking you anything on the final project about it. So you might say, why are we spending any time on it at all? And the answer to that is, we have all these equations. We have what you're going to learn over the next couple of weeks is that, unlike what we learned in mechanics of materials, in a real system, stress is a differential equation, strain is a differential equation. There's also equations that we never even talked about in mechanics of materials that help you ensure that your strains are physically real. Meaning, when you solve differential equations, it's possible that a solution might be that you pull on this beam and you're like, okay, what's the deflection at every point in the beam? You pull on this beam and the math might spit out like, sure, what happens is the beam stays the same shape and a bunch of holes pop up everywhere. Well, that doesn't happen in real life, but it can happen in your math. Those conditions about putting restrictions on your strain are also differential equations. So stress, strain, and what's called compatibility are all differential equations. Most of them are partial differential equations and nonlinear partial differential equations. And that's a problem because we don't know how to solve nonlinear problems, as we've talked about. We don't really know how to handle most nonlinear problems either. And what we do is we rely on computational mechanics to solve these types of problems. But computers really struggle to solve differential equations. It's a really hard requirement for something that has numerical flaws, like limits, physical limits on numerical precision, to solve a differential equation, which requires that this equation be solved at every single point in this body and be exactly equal to 0 at every single point. And so what is done is people solve a different equation. And so the reason why I'm lecturing you on this topic today is because the stuff we're going to cover today is actually what all your commercial finite element solvers are solving. This is the equations that they're solving. This is what's going on under the hood. For the most part, you may or you may not interact with these things, but I feel like you need to know that this is what's happening under the hood. And so if I were you, I would kind of think of this as a curiosity of like, okay, this is what's happening under hood. This is how the thing works. If you go off and get really into finite element simulations and you work at a company like Abacus or doing stuff with MathWorks and Matlab, these things will come up again. If you don't, you at least know what's actually happening under the hood. This is actually what's going on when your computer is solving things. And so I don't know if that's the most exciting motivation, but I feel like it's important for you to know what's happening under the hood. So take this lecture as let's say things you can file away. But this is not going to make or break your semester. This is not something that I need you to know to get an A in structural mechanics. This is kind of something I need you to know because if you're using finite element software, which many of you will do going forward, this is actually what's happening. And so, as I've mentioned, are governing the field equations of solid mechanics are differential equations, and they're generally nonlinear. They're hard to solve. And we've already solved one. So the one we just did in our homework was, we'll use that as our example. So we'll use that problem that we just solved on our homework as our example to motivate what we're doing here. And what we're going to derive are what are called weak formulations or weak forms. And the idea is we don't want to solve differential equations. We want to solve something that's easier for our computer to handle. So let's take our equation. Let's take EA times U double prime of X minus F of X is equal to 0. We can just say, let's define this equation. Let's just call it something. I'm going to call it R of X. So I'm going to call this equation R of X. And we're going to call this, the reason why we're using it as R is we're going to call this our residual. So really compactly, we could say that our residual has to equal 0. This equation, to solve our problem, this equation must hold for every point over the elastic body. So this has to be true for all X between, say, 0 and L. This requirement that our residual be equal to 0 at every single point in the body is what's known as the strong formulation or strong form. It's very, very strict. Every single point in the body, this equation has to be solved and be exactly equal to 0. That's a huge problem. And if you've ever done anything with computers, have you ever heard about, anyone's heard of chaos theory? Like the butterfly effect. The butterfly flaps its wings over here and it creates a monsoon somewhere else over here. It's the idea that small changes in your initial conditions, incredibly small changes, like you solve a problem and you set the initial velocity equal to 0, and you get one answer. Or you solve a problem and you set the initial velocity to 1 times 10 to the minus 15, kind of sounds like 0, and you get a completely different answer. This is at the heart of dynamical systems. But the reason this was found is because people were just solving equations using their computer, putting in the initial condition was 0, but your computer was like, actually, I'm going to use 1 times 10 to the minus 15 or whatever. And it would pick a very, 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 very small number. So you think you're solving this equation, and you're going to get the same answer every time because you put in the same equation every time. But if the numerical value changes just ever so slightly, you get a completely different solution. This has to do with the way our computers handle numbers. There are just kind of precision elements to how we handle numbers in a computer that makes it really hard to actually get 0 or to actually get a number to be exactly what we want. If you ever done anything in Matlab and kind of dealt with the differences between integers and floating point numbers, like these floating point numbers for your computer come with some precision attached to it. What all of this means is that to ask our computer to solve this equation and have it be equal to 0 at every single point, not equal to -1 times 10 to the negative 15, but equal to exactly 0 at every single point in the body, is incredibly hard. And it leads to your simulations not working, especially when you have nonlinear problems, which we have, or boundary value problems that are involve partial differential equations, which we also have. So we want something that's, let's say, a less strict restriction on how we solve this equation. And the idea is, well, we don't need it to be exactly equal to 0 everywhere. What if we just said that let's allow the average be equal to 0 over some small distance? In a sense, it's kind of the same. Instead of being exactly equal to 0 everywhere, we just say, okay, between these 2 points, if we just average between those 2 points, then it's 0. And so mathematically, what this means is that we say, let's take our residual and multiply it by something, some function. So let's take our residual, r of x. We're going to multiply it by something. That's something we're going to call v of x. And we're going to give this thing a name. We're going to call it the test function. It's also called the weight function. And instead of saying that we need r of x equal to 0, we're going to say that we need the integral of r of x times our weight function, or our test function, to be equal to 0. And I'll remind you, I'm gonna be like extra pedantic here. This is our equilibrium equation which you could have solved for using variational calculus like you did in your homework last night. That's this equation. You put that equation that you got from your variational work, multiply it by a test function, and then integrate over that and let that total integral be equal to 0. This quantity here, this integral, is called J. All right, so let's actually like implement this and see what this thing looks like. So we know r of x. So we're going to remind ourselves that we're actually trying to solve a particular problem. We're trying to solve this thing. So we can take J and say this is going to be equal to the integral from 0 to L of EA u double prime of x minus f of x times v of x dx. That integral needs to be equal to 0. We know a couple boundary conditions. We found these last night. We found these boundary conditions in our up here, right? So there's 2 boundary conditions, this one and this one. This one says there's no deflection at the clamped end. This one says there's no force, point force pulling on it at the free end. So these are still the boundary conditions we use. And what you do is, and this is something you will interact with, and you might have already interacted with when playing with finite element software, is kind of choosing the form of what are called the shape functions in there. If this doesn't sound familiar to you, it basically is saying if I have two nodes. So you got a mesh. You have this big mesh that you use to kind of split up your problem into tiny little parts. And the way those mesh points are connected, there's some nodes there. And you kind of what's called interpolate between them. You say, I'm going to solve the equation here, I'm going to solve the equation here, and I'm just going to kind of make some connection between those two. The simplest connection you could do would be to say that they're linear. Like I have the answer here and I have an answer here, I'm just going to draw a line between the two. What is more common is you might use different types of polynomials in there. There's all sorts of crazy names for things, Hermite polynomials and they're quadratic polynomials and all sorts of other function you can use. But the idea is you have 2 points, you solve for them at these 2 points and you interpolate between them. And so we're going to use guesses for our u of x and v of x. We're going to let u of x and v of x be quadratic polynomials. And again, just like we've been doing in the past, we just basically write down a quadratic polynomial. What's a quadratic polynomial? It's some constant plus another constant times x plus a third constant times x squared. So what does that mean? It would look like this. We'll say that u of x is equal to a naught plus a1 times x plus a2 times x squared. And v of x we'll give it b. And these, again, we know that this is kind of our weight function or test function. And in the FEA world, the guess that we made for u would be referred to as the trial function. What we're doing with a little bit more detail that is probably not worth me going into is referred to as the Galerkin method, which is something you may encounter if you're doing finite element work. It's a method for solving structural mechanics problems, essentially. More broadly than that, but. All right, so we have an equation. We have our guesses, and we just insert u into here, and we insert v into here. This is easy in that we can do this by hand. So, we're going to actually work this problem and get an actual answer for what u is. But typically what you're doing is you're implementing this, in your code and having your computer solve this. So take a second and calculate the second derivatives and actually do this. Take a second and tell me what j is. So you got to put in u double prime, put in v, and then integrate over L. All right, maybe folks got something or on the way to getting something similar to what I have here. I kind of coupled them so you can see where stuff comes from. So this term here comes from our residual, and this one comes from our test function. And the product of these two things has to equal 0 in order for us to say that our, whatever we want to call this, our j is going to be equal to 0. We're going to do something here that is really familiar to us, and that familiarity is going to become even richer in the next little bit here. You're going to start to hopefully make some connections to things that we've done in the past. But what on earth are we doing? We just multiply our actual differential equation by some made up thing that was some polynomial function that we also made up. How on earth is this actually useful or allowed? Like, how can we just do this? So this comes from mechanics. We like derive this, we derive this by doing variational methods of minimizing the total potential energy. And we multiplied it by some random thing. And then we integrated it and said the integral of this thing times this thing has to equal to 0. How does that work? Well, it works by saying, well, if this thing is some arbitrary thing that we just made up, then this quantity should be 0 no matter what arbitrary value of B0, B1, and B2 we choose, because we just made it up. So how can we expect it to, we threw in some random function there, but what we're going to say is that, well, if we could just throw in some random function, some test function, so that way we can integrate over some domain, then that test function, which has some unknown coefficients, these better be arbitrary. Our solution better not depend on these arbitrary constants of this thing that we threw in there. Which means that J must vanish for any arbitrary choice of our constants B not B1 and B2. Which means that all we're left with is this thing. So I would say, therefore, oh wait, where did the Q come from? Oh my gosh, I totally changed my stuff. It's not supposed to be a Q, it's supposed to be an F. Sorry about that, everyone. Oh, I know what I did. Okay. I skipped a step. Yeah, I said let's, what I forgot to tell you was let f of x be a constant. So we don't have to worry about it for the integral. Usually you know it, it's like your force distribution. So I'm just saying, so I meant to say let that be a constant. That way when you integrate it, it just stays there as a value. Sorry about that. So that means this. Why are we doing this? Just like we did for the approximate methods with Fourier series, polynomial series, the Ritz method that we discussed, we just guessed our solution. We guessed that our solution for u was going to equal a naught plus a1 plus a2. And look, now we have an equation that involves only a2, so we can solve for a2. So we just found one of our three unknowns in our equation there. So a2 is equal to negative, no wait, did I have a sign change? I did have a sign change. All of a2 is equal to f naught over 2ea. How do we find these two?
Can we use boundary conditions?
Yeah, perfect. We have two boundary conditions. We know the deflection and we know something about u prime. Here's something that's super weird and should make like alarm bells go off in your head that something's wrong. In order to solve for these two constants, we have to apply our boundary conditions in a specific order. That's not good. That's a problem. That never happens, right? We usually like, you have two boundary conditions, you have two unknowns, you can solve them however you want. You solve them simultaneously. But in this case, we have to apply them in a certain order, which tells us that we're probably doing something wrong. We're going to do it anyway, and then we'll take a break and I'll tell you what we did wrong. But though we apply our two boundary conditions, and we know that the deflection u at 0 has to equal 0, which tells us obviously a naught has to be equal to 0. And we can then apply our other boundary condition, which was that EA prime of L is equal to 0. Remember, that's the natural boundary condition you found by doing integration by parts in the calculus variations last night. So that's the boundary condition that we derived, whereas the top boundary condition is the one that we kind of have was imposed by geometry. We solve this one and we get that A1 is equal to F naught L over EA. And so the end result is that the deflection of our beam is equal to F naught over 2EA times X 2L minus X Okay, this is what's happening here. It's telling us what the stretch is, what the displacement of material points are along our beam when this beam is experiencing a distributed load. So you have some beam from here to here. You want to know what the deflection or the displacement is at every single point along that beam, depending on the magnitude of that uniform distributed load F naught, and depending on the beam stretching rigidity EA. We have an equation for it now. It says it's going to go as F naught over EA, and then it's going to depend a little bit on where you are. It's going to have zero deflection over here, and a lot of deflection as you go linearly going this way. So it worked. We solved our equation. We solved it in a way that is really friendly for our computers to solve it. Although there are a couple things that are weird. One is that we had to apply the boundary conditions in a particular order. Another thing that's bad for your computer is that U and V enter at different orders of derivatives. U entered as U double prime, V was just V. That's tough for computers because you need to pick functions that have what's called the same continuity. Continuity means like how many times can I take a derivative of this function and still get something back. So if I take 3 derivatives of my test function, we're kind of in trouble. It's a second order polynomial. We lose things there. That issue of having those things be at the same order is really important for solving problems, especially problems that involve slender structures, shells, plates, where you have to really be thoughtful about the number of kind of derivatives that your test function can take. Okay, so the boundary conditions are weird. The fact that U double prime and V are entering at different orders is weird, and both those things are not just weird for like us to wrap our head around, they make it hard for our computer to solve something efficiently. So we would like a better way of being able to implement this. Let's take a break till like 10:05, and then we'll iron out these issues.
Professor,
Yep.
can I just ask real quick, what was the point of adding the weight function? Because didn't it kind of just go away?
It does kind of go away, but it is essentially a way that we can do this averaging process over the domain, and also do this averaging process in a way that is, let's say, arbitrary. Like in a way that it shouldn't depend on the way we choose to weight it. And so it's kind of like a, well, I'll kind of give away the ghost here. It's equivalent conceptually to the idea of a virtual displacement. So it's the same idea, and we're going to show that mathematically in a little bit, that like the test function is essentially the virtual displacement. It's just a virtual displacement field. And so we use the virtual displacement and the principle of virtual work to say, Well, I can add an arbitrary displacement and I know that my virtual work has to be 0. Because it's a fake, just a pretend displacement. The same thing is true here. We're using this as like a virtual displacement acting on our differential equation. It's actually, I'm gonna show you towards the end of the lecture that this basically takes the same form as what you would get if you did the calculus of variations on this problem. And what that means is that all the work you did learning the calculus of variations, being able to calculate the first variation, you're actually calculating the weak form, which is what you can plug into your computer to have it solve. It's probably only partially answering your question, because I would imagine that the fact that we can multiply, I would imagine that it's still a little bit of a mystery why the virtual displacements in the first variation works kind of at all. And so I'm probably only partially answering your question, but the idea here is we are using some virtual displacement, in this case virtual displacement field, to ensure that since that virtual displacement is arbitrary, whatever multiplies that virtual displacement ends up being the quantity that we have to solve for. So I don't know if that's.
Yeah, no, that helps. I think, yeah, I understand. Looking at it like the virtual displacement thing, I think helps.
And we're gonna do that. I'm gonna show you that it's the same thing you would get if you do that. It's just yeah. All right, so we have a couple of problems we want to iron out. It turns out both those problems can be ironed out by doing one thing. And so the problems are what? The first one probably doesn't seem like a problem to you, that u has a second derivative and v has no derivatives. There's no real reason for that to be obvious why that's an issue, but it has to do with the fact that the choice of our guess for u and the choice of our guess for v will end up having different amounts of times that we can take derivatives of them. That while that might not seem like a problem here, it ends up being a problem for computationally solving these equations, and we would like to have them be at the same order of derivatives. We would like to have either u double prime v double prime or u prime v prime. We want them to match up and be at the same order, because that will be easier for our computer to handle. We can just give it one function, one guess, some polynomial or whatnot, and then it will not have any issues with, oh, this one needs, I need multiple derivatives of this one and no derivatives of this one. It probably doesn't seem like a big issue, but it's something that we would like to resolve. And as it turns out, resolving that problem is also going to resolve our other problem, which is really weird, but you probably don't know where it comes from. And that is the fact that you have to apply the boundary conditions in a specific order. We really don't want that. We don't want it because we don't necessarily know offhand what order we should be applying the boundary conditions. As the problem gets more complex, it's not like it would be very easy for us to say, okay, first apply this boundary condition, solve for that, then apply this one. It might change depending on the complexity of your problem. We don't want there to be, and there's no physical reason why there should be. It's a differential equation. You just need to satisfy the boundary conditions. You don't need to satisfy the boundary conditions in order. And so, as it turns out, we can solve both of these problems by doing the same thing. And that is getting J to be balanced, which means that derivatives of u and derivatives of v appear at the same order. Okay, and so J is what? J is the integral from 0 to L of EA U double prime. We're going to stick with this just being a constant for now. Multiply that by our test function. That's got to equal 0. So clearly right now, they are not at the same order. It's 2 derivatives on U and 0 derivatives on V. How do we fix this? You know the answer. That's a reasonable guess. Like, why not just start with a test function that's already of the same order as u of x? And I don't know why we don't do that. I don't know why we don't do that. So I will have to figure out the answer to that. It's a good suggestion. Yeah, that's a very reasonable guess, and I don't have a good answer to you at the moment as to why that doesn't work. So we're gonna just put that on hold and try a different one, and then I'll try to figure out why we don't do that. Integration by parts, exactly. Yeah. So if we integrate by parts, we will, well, if it's not obvious to you yet, it's how we kind of removed an order of derivative on our virtual displacement or virtual slope in the past. But as you recall, that also added a derivative to the other terms. The integral of u dv is equal to uv minus the integral of v du. So we ended up getting a derivative of the other term. So take a minute and derive the balanced weak form here by integrating by parts. All right. So you're all becoming professionals at integrating by parts by now. So hopefully you all got the same thing as me. I got this. Integral from 0 to L of EA times U prime of X, V prime of X, dx. You could have kept this in the same integral, so if yours looks a little different, it could be equivalent, but I have pulled out F naught times V of X. If we hadn't assumed F of X was a constant, we could have had F of X there. That's also fine. And of course, we also have our boundary term appear. We knew this boundary term already. Had we not, had we only had the governing differential equation, say maybe we got that governing differential equation not by calculus variations, but maybe we got it by a force balance or moment balance. Well, then now just by doing integration by parts on our balanced weak form, we have found our natural boundary condition. And now our computer is happy because U enters as U prime, V enters as V prime. Why does that matter? It matters because the smoothness, which is basically how many times can you take derivatives of your guess function, smoothness requirements are the same. We also got a natural boundary condition for free. Now we can apply our boundary conditions whenever we want, either at the beginning or end of solving the problem. And we would refer to this thing that I'm highlighting in yellow here as our balanced weak form. And this is what your computer's solving. This is what all your finite element solvers are doing. Whether you know it or not, they're solving the balanced weak formulation of your problem. And they're solving this balanced weak formulation for primarily computational reasons, meaning this balanced weak form allows the same continuity of our guess functions. We need these guess functions because we have to solve our problem at every node. And we need to interpolate between those nodes. So we need to kind of tell it how to interpolate between those nodes. Our computer finds this easier to solve as well because as we're trying to make requirements on our governing equation, by doing this integration of that equation, setting that equal to 0, it's solving a much simpler problem, which is just to say, as I integrate between two nodes, I just need to make sure that on average, that thing works out to be 0. And do that in between every node. On average, this quantity needs to be 0 here. That's a much weaker requirement than the strong formulation, which says that at every single point in my body, my quantity of my differential equation needs to be exactly equal to 0. So this is what's happening under the hood. And the fact that we have kind of noted that our test function contains arbitrary constants, and that we can balance our weak form, which is the integral of the product of our residual times our test function. We can balance that through the use of integration by parts. So we have an arbitrary displacement, integration by parts. The weak formulation is very, very closely related to the principle of virtual work and the tools that we've developed for the calculus of variations. And so let me just lastly show you that, just for clarity. If we ensure that our test function is some admissible variation of our, say, displacement field, so u of x. What do I mean by admissible variation? What I mean by that is exactly what you're used to me saying when I talk about the principle of virtual work, is that as long as I ensure that my test function doesn't vary in places where it can't vary. So can't be arbitrary somewhere where it's clamped. That would be an inadmissible variation. To say, I'm trying to solve a problem, I have a clamp at x is equal to 0. We can't allow us to have a test function that varies the location of that point at x equals 0, because that is fixed at exactly 0. So by admissible, we mean the exact same thing we mean when we talk about the principle of virtual work, which is that you can have an arbitrary displacement on your particle or your material point, unless that particle or material point is constrained. So if we take our test function to be an admissible variation of u of x, mathematically that means v of x is an admissible variation. Variation means first variation, delta. So if v of x is an admissible first variation of u, then j is equivalent to the first variation of our total potential energy. So for instance, if I had just said my total potential energy is going to be my strain energy, so EA over 2 times the integral of my strain squared dx minus the work being done. What's the work? The work is going to be f of x times u of x times the integral from 0 to L dx. The first variation is then going to be equal to EA times the integral 0 to L of U prime delta U prime Let me just move this thing. I'm going to tuck it inside the integral. Even though we don't need to. It's constant. And note the similarities here between this and what we've done up here. We can. I didn't integrate by parts yet, but we could do that to get the boundary term as well. So we don't have this one because I didn't integrate this thing by parts. But obviously I could integrate this thing by parts and we would get this with this boundary term as well. So the kind of key takeaway that I want you to have here is that the calculus of variations allowed us to do three things. This is the most important part. We're going to end after this. The calculus of variations allowed us to do three things. One, it allowed us to derive the governing differential equations and natural boundary conditions given a potential energy. Two, it allowed us to use approximate methods like the Ritz method or the kind of Fourier series approximation for us to immediately guess the solution or the form of the solution and then use the variational principle, calculate the variation of our total potential energy, calculate the variation or of our strain energy in our work to approximate our solution. So we, one, derive the governing differential equation in natural boundary conditions. Two, use it to develop approximate solutions to our problems. And three, by deriving the first variation of our problem using the calculus variations, we have exactly what we would input into our computer to solve computationally. Many of you might be familiar with COMSOL. I use COMSOL a lot in my research. One of the things we do, though, is we don't really use any of their built-in modules. We just use it to solve the equations we derive. And the equations and you can input into COMSOL the weak form directly and ask it to solve the weak form for your problem. And the weak form is just what we derived using the calculus variations. It's equivalent to the first variation of our total potential energy. So this kind of the mathematics that we worked on are really central to a lot of problems in structural mechanics. They give you the equations that your computer solves in a finite element solver. They give you the governing differential equations and boundary conditions that you might be able to solve analytically. And they give you a way to approximate solutions to problems by making a guess as to what the form of that solution looks like. That's pretty powerful. Questions? Concerns? Again, this lecture was really meant to just connect the dots for you. Just to connect the dots between variational calculus and kind of the magic black box that's going on under the hood when you click like on SolidWorks or something. This is what's happening. It's solving this equation. And it's solving it at every node and interpolating between the nodes and kind of telling you, okay, at this node, the stress is going to be here, and at this node, the stress is going to be here. And that pretty color rainbow graphic that you get at the end, which is showing you maybe the stress or the strain. What it's doing is it's calculating those things at every mesh point and interpolating between the mesh points. And to do that, it's solving these equations. We're going to do two things. We're going to get into the weeds on the differential equations that describe a solid object. I mentioned that stress, the equilibrium equations are actually differential equations, and the kinematic equations for strain, as we've already kind of seen, they're differential equations. We're going to use those, we're going to derive those so that you're aware of what they are, and then we're going to solve some problems. Instead of dealing with just 1D structures, we're looking at 2D axisymmetric things, so disks and pipes and stuff like that. And then the last portion of this course is going to be, we're going to write up our own finite element formulation in Matlab. Very basic. We're going to solve very simple structures, trusses that have elements that can stretch or bend. But these are the kind of 3 portions of this course. The one bulk of it is like a lot of these energy methods. And then the last 2 are going to be kind of equilibrium methods, where we start with like kind of stuff that you're familiar with, force balances, moment balances, stuff like that. Sound all right? We're done a little early. I will send out the midterm. Please try your best. And yeah, have a great weekend.